To be here. So I wanted to talk about some themes from ideas from quantum field theory, in particular from quantum gauge theories, and how they are affecting representation theory in particular. So trying to make connections between 3- and 4-dimensional gauge theories, which have had a lot of success in low-dimensional topology, but are now starting to see connections to basic structures in algebra. And so I wanted to start with kind of a toy model where we're just going to think about, talk about the idea of a finite dimensional vector space as a kind of a warm-up. So I want to think of a finite dimensional vector space from the point of view of one-dimensional topological quantum field theory, or just topological quantum mechanics. And so this is what's the idea here. I'm going to start with studying, and I apologize to those of you who heard the same last week. But I want to start with a kind of a model where I'm going to think of one-dimensional, time-dimensional theory. So I'm going to attach a vector space V to this kind of picture. I have an oriented one-manifold. I think of the V as my Hilbert space of some kind of particle theory in one dimension. So given a one-dimensional, given a finite dimensional vector space, I'm going to start drawing pictures of oriented one-dimensional manifolds. And I want to see how these pictures of oriented one-manifolds capture properties of the vector space V. So as a physical theory, this is very silly. This is going to be a theory with a Hamiltonian zero. So the time evolution is going to be trivial. So this vector space V sitting at this point kind of moves along, and nothing happens to it. So the map from time evolution map from V to V is just the identity map. But we can start drawing slightly more interesting one-manifolds. So for example, we can draw this time, reverse the direction of time, and we have another vector space attached to this picture. We're thinking of vector spaces attached to oriented one-manifold. This is another vector space, which I'll call V dual. And we want to see that this really is the dual vector space. So we see what kind of interesting topological time evolutions we can have. Well, we can talk about a manifold like this, where time kind of loops around. And the basic rules of the game is here I'm going to attach my vector space V. Here I'm going to attach the vector space V dual. And I have an evolution that starts from V tensor V dual and goes into the vacuum. So I think of this as a map from V tensor V dual to the complex numbers. Well, if I think of V dual as really being the dual vector space, there's a natural such map, just the evaluation of a covector on a vector. I can also draw a picture going the other way. So if I have an evolution like this, and I have a map from V that goes from the vacuum to V tensor V dual. Now, this map is a little harder to see writing it as V tensor V dual, but if I identify V tensor V dual with matrices, with endomorphisms of V, then this map is just the inclusion of the identity. Now, here I'm using something non-trivial about the vector space being finite dimensional. If I take an infinite dimensional vector space, I can't write a map like this, V tensor V dual, not one that's satisfying the constraints that I want. So what kind of constraints do I have? Well, for example, I can draw this Markov-Zorro picture as one-dimensional manifolds. These are the same oriented one-dimensional manifold, which means that if I think of this, so that gives me an identity between a map from V to V, tensor V dual, tensor V to V. And this composition of these two maps in this way has to give the identity. So this actually gives you a very, if you just abstract these notions and put it in a kind of much more abstract setting, a setting of a symmetric monoidal category, this gives a notion of a dualizable or finite dimensional object. In any case, one thing we can get out of this picture is the one invariant, which is there's only one closed oriented one manifold here, which is the circle. And to this, I get a composition, which I go from C to V dual tensor V to C. So this is the evaluation, or the trace, and this is identity map. So what I get is the dimension of V as the invariant attached to the circle. So these kind of caricatures, these kind of pictures allow me to characterize the notion of finite dimensionality. A vector space is finite dimensional if and only if there's another vector space with such maps satisfying this identity, and the one invariant of a finite dimensional vector space, which is the dimension. OK, so this is not very exciting either physics or math. So now let's try to make it a little more interesting. So now I'm going to go from 1 dimensions to 2 dimensions. So I'm going to try to talk about, I'm going to fix a group, and again, this is still going to, in the category of toy models, I'm going to fix a finite group. And I want to say, what can you capture about the classical representation theory of a finite group from the point of view of topological field theory? So what I'm going to attach to a finite group is a 2-dimensional, or if you like, 1 plus 1 dimensional, 2-dimensional topological field theory, which is the topological Yang-Mills theory in 2 dimensions. It's topological limit of Yang-Mills. Or this toy model was also studied in great detail by Dycroft and Witten. So what is this? So this is going to be a 2-dimensional topological field theory, and what I'd like to explain is how you can kind of recover much of what you would see in an elementary course on representation theory just by drawing pictures of low-dimensional manifolds. So what can you? So first of all, in this topological Yang-Mills theory, my fields. So I have a notion of fields on space-time, and my fields here are going to be. You can write them as principal G bundles. Or you can think of them as principal G bundles with connections or flat connections on my space-time. But since my group G is finite, having a principal G bundle, having a flat principal G bundle, having a G covering space, or having, well, there are several other things, or having just a representation of the fundamental group of my space-time into G, these notions are all equivalent. I have just a discrete covering of my space-time, which is with structure group G. So it has several different pictures. So this is going to be my space of fields. And to define the field theory, I'm going to any 0, 1, or 2 manifold, I'm going to attach an invariant. And that invariant is going to be a linearization of the space of fields on that manifold. So I'm going to look at the space of fields and attach to it some linear invariant. So let's start from the top, which will be kind of the opposite of the theme of the talk. We'll see that mathematically it's much easier to build these topological field theories starting from the bottom and up. But what is this topological field theory? Let me call it Z sub G. It's going to attach, first of all, to if I give you a closed, say, oriented surface, I'm going to attach a number, kind of partition function on this surface, which is just going to be the count of the number of these G bundles. Just count the space of fields on sigma. So this is some finite set. These are bundles with symmetry, so I have to count this, keeping track of symmetries. But this is going to be the invariant. It's going to be my kind of finite path integral on a closed surface. There's a little more structure if I go next to the level of the circle. So what's the idea in the circle? So here, I'm thinking about this really as a cylinder. Really have so this is going to be my time evolution on this circle. So I think of this as the Hilbert space of the theory on the cylinder. And so what is this going to be? Well, it should be the rules of the game are going to attach to this. My Hilbert space is going to be functions on fields. The way I'm going to linearize the space of fields on the circle. So fields on the circle, these are principal G bundles on the circle. They're given by a single element of G up to conjugation. So I'm going to use this kind of notation to denote conjugation action. So these are, in other words, they're conjugacy classes in the group. So functions on the space of fields. So in other words, I'm going to look at complex valued functions on this finite set. So these are what you'd call class functions on the group. These are functions on the group that are invariant under conjugation. OK, and now by looking at various 2 manifolds, I can, with various topologies, I can get various structures on this vector space. So a priori, it starts as a vector space. I can draw versions of these pictures, kind of take the pictures I'm about to erase across the circle, and find out this vector space is finite dimensional, which is not a great discovery. It's functions on a finite group. But more interesting structures we can see is we can give. So I'm not going to go in detail, but if you draw various pictures, for example, you draw one interesting manifold with boundaries, the pair of pans. or sometimes topologists like to draw it looked at from above. And this gives us an evolution starting from two copies of this vector space to itself. In other words, a multiplication, which is, from this picture, is easy to see as it has to be a commutative associative multiplication, just because of the topological invariance of these structures. So I find that the class functions have a natural commutative multiplication, which is something I learned in representation theory pretty quickly. I also found out that they have a non-degenerate trace. So they have a unit. This is a map from C to my space of class functions. This time, and I also have a trace, which gives a map the other way. And together they form a commutative, what's called a commutative Frobenius algebra. So this is one part of the structure that one can see out of the field theory pictures. But the representation theory comes into the game more clearly when we go one level further. So when we go, I want to think about, from the language of extended field theory, I'm going to think about what happens to points, or from the point of view of the field theory, I'm going to study boundary conditions. In fact, I'm going to study local boundary conditions in this two-dimensional field theory. So I can ask, what are possible local boundary conditions in this field theory? So what does it mean, roughly, just in terms of a picture? I'm thinking of looking at something I can put at a boundary of a surface. So this is going to be an example of a boundary condition, something that I can attach to such a picture. So I have a little half space, and I have a vector space moving along. So why am I saying vector space? Because if I think of a boundary of a boundary condition, this is local boundary conditions themselves. First of all, they would form one-dimensional topological field theories in the sense we had before. So if we thought of a boundary condition kind of decoupled from the gauge theory, decoupled from bulk theory, just in and of itself, this boundary condition is something that lives on one manifolds. So if you could decouple it from the main theory, you would see just a one-dimensional, just a quantum mechanics living on this boundary. And we decided that this is the same thing as a finite dimensional vector space. So kind of in the abstract, what lives on this boundary is a finite dimensional vector space. But we have to couple this to the theory. And so these are one-D topological vector space, which are coupled to the gauge theory. And there are many ways to say that. One way to say is that if you look at principal bundles on this picture, there's only one of them. This is a contractible picture, so there's only one bundle here, but it has automorphism group G. So this vector space should carry the automorphisms of G. So in other words, this vector space should be a representation of G. So let me kind of take this as a hypothesis for now, that what this theory attaches to the point, which is the extended field theory language for the collection of boundary conditions, and this is going to be the collection of representations of the group G. So given any representation of the group G, I can make a local boundary condition for this theory. So these now form a category rather than a vector space. That's the structure that's inherited by these local boundary conditions. So you can ask, for example, why is there a category? A category means I have not just these objects, not just these potential boundary conditions, but I have maps between them. And so, for example, if I give you two different boundary conditions, let me call them, say, V and W, I can draw a picture like this where I put my theory on a strip where I think of V living on one side and W on the other side. And the invariant attached to this picture, it's kind of the Hilbert space of the theory on this strip, is a vector space, which is just the space of maps as representations from V to W. I'm looking at vector spaces and map, or in extended field theory, you might draw it like this. You take an interval where you decorate the two boundaries with two different boundary conditions. And now to this picture, we attach a vector space.
To the right both?
Yeah, I mean, I'm just thinking of this as two boundary conditions. Look at the Hilbert space of the theory on the strip with these two conditions.
Right. The W is to the right, and B is really to the right?
Yeah.
To the left.
It's to the right. So this is just, I'm looking at the theory on the strip cross R. And I'm getting a vector space out of the theory on the strip cross R. And this vector space, or this picture, I would just draw it as V and W.
Physicists consider V or W as Trumpeter factor, then usually
I would draw it the other way.
yeah.
Okay. Well, I guess the orientation, certainly the orientation induced, yeah, sorry, you're probably, of course, your orientation induced from the interior is yeah. Yeah.
I think I would think that a boundary condition is something you would assign to the, maybe the vector space should be assigned to the boundary, the codimension one thing. Why are you assigning it to the point?
Well, this is a local boundary condition. This is something that's allowed, this is a whole local field theory that lives on the boundary. So this is something that makes sense to give just a segment of boundary. So I'll explain the picture that you're talking about in a second, how that appears.
I see. So I think of V as being kind of a local boundary condition is basically given by a vector bundle. V is like the vector bundle at every point.
Yeah. So let me give so how would you see such a boundary condition in nature? And so you could ask, I mean, the natural way to get, so this is some abstract collection of all possible quantum boundary conditions. One way you could get such a boundary condition is finding them in geometry, so by putting a boundary condition on actual fields. So we have these gauge fields. In the surface, we can actually put a boundary condition on fields. So how would I say that? So how would I put boundary conditions on my fields? So let's give an example. Suppose I give you a subgroup of G. So then I correspond to a subgroup. I have the set of cosets G mod K, which is a G space. For what I say, I can replace this by any G space X. So suppose I have a space on which the group acts, for example, G cosets. Then I can make an actual boundary condition on the fields, which is I can ask for fields that on the boundary have their symmetry broken from G to K. So I can look at a picture where I look at so along this edge, so I have a G bundles in the interior, and along the boundary I ask for the reduction of their structure group to K, or I break the symmetry to K. So that's some extra structure you can put at the boundary, and it gives us a natural boundary condition on fields. And so how would this correspond to this language of representations? Well, given a subgroup K, I get a representation which is functions on G mod K, the linearizations of the space, or more generally functions on any G set X. This is naturally a representation of the group. So this is sort of my main source. So if you like, this is the geometric construction of representations. You can ask, where do representations come from in nature? They come from functions on G sets. So for example, there's a lot of games one can play like this, and the claim is somehow that you can reconstruct much of classical representation theory very nicely in these pictures. So for example, one thing you know in representation theory is that representations of the group are the same as representations of a linear object, which is the group algebra. So you can take linear combinations of group elements. And that appears very naturally in this picture. So I'm going to look, for example, I'm going to look at a picture where let me draw it this way. So suppose I have this is a particular boundary condition, which is going to be take my G bundle and I take a trivialization. So this is the case K equals 1. Trivialization on the boundary. So this is, I break the symmetry group completely. So I can look at G bundles where on the boundary they're broken down completely to identity. So if you look, for example, what is the space of G bundles on an interval on which you've broken the symmetry group down completely at both ends, this space of fields is just a copy of the group G. And so the vector space I'm going to attach to it is functions on G, which is what I call, which is the group algebra. So the group algebra is just the vector space I attach to G bundles with trivialization on both boundaries. And the fact that it's an algebra can naturally be seen just by writing an evolution like this. So I start with two elements of the group algebra and evolve them through time, and I get another element of the group algebra. So this gives me an associative multiplication structure on this group algebra, which now has no reason to be commutative. In fact, isn't commutative. And more generally, given any other boundary conditions, if I have my favorite boundary condition V, I can see that it's a module. I get a module over the group algebra just looking by putting the trivial condition on one side, putting the V on the other side. So this is the vector space V thought of just as a plain vector space, and you get this carries an action of the group algebra. So this gives an action from group algebra tensor of vector space V to itself. So it recovers the action of the group algebras on representations.
Interval, there's only one G bundle, trivial one.
Sorry?
Can you explain this computation where you use?
So here I'm looking.
Intervals is just trivial. So.
Well, no, but it's actually structure. So if I gave you just a plain undecorated interval, or then the G bundles on it, there's only one, the trivial one, and it has automorphism group G.
Oh, I see.
But now if I look at a boundary, if I look at a, so let's maybe draw a picture. Like suppose I give you two subgroups of a group, for example. I can look at bundles. Let me kind of draw a picture like this. Let me give them, I guess I should give colors. Suppose I have a red boundary. This is the red and this is orange. So I can look at an interval where one side is red and the other side is orange. So what does this mean? This means I look at G bundles on this interval. And you say, of course, there's only one. It's trivial. But I'm going to add the structure of reduce the structure group to K on one end and to B on the other end. And you ask what the space of these things is. And now you all of a sudden have some non-trivial structure. The space of gauge fields on this is just, you can write it as a copy of G mod K on one interval, a copy of G mod B on the other end, but there's a G symmetry in the middle. So it's really this product. Or a nice algebra computation, this is the same as double cosets for K and B. So just the space of fields on this picture is the double cosets for K and B. And this picture in particular, you can use this, for example, to understand what are maps of representation. So I said that on the other hand that this picture is supposed to capture maps between two representations. So on this side I had the representations, which is functions on G mod K. And here I have functions on G mod B. And I can ask a question, a pure algebra question. These are called the induced representations. I can ask what are maps of representations between functions on G mod B, say, and functions on G mod K. And I have to get the orientations right, as Kentaro pointed out, to set this up. So I want this one going this way, this way. So I ask, what are functions between these things? And you ask, well, this is a nice matrix calculation. If I have functions on one set and functions on another set, maps between them are just matrices. They're just functions on the product. And, well, but I want a map of representations. That should be a function on the product that's invariant under the common action of G. So these are what are called intertwining operators. So maps from this representation are the same as matrices. In other words, functions on the product, which are invariant under the common action of the group. Or in other words, functions on double cosets. So this is a well-known fact in algebra. This is how you write intertwiners between induced representations. Or if I take K and B to be the same, in the case K and B to be the same, I find that this space of double cosets is an algebra and is the same as endomorphisms of this particular representation, G mod B. This is what's called a Hecke algebra in representation theory. So you can see the pictures of Hecke. So that means an interval with both endpoints orange. And then I can define a multiplication just like there, just by carrying the orange boundaries along. So I just draw this. So this gives you a crash course on what Hecke algebras are. Hecke algebras are exactly algebras like this. They're endomorphisms of these induced representations. And they get this multiplication just by just putting the gauge theory with this boundary. So one can play a lot of games like this and recover any of your favorite topics in kind of abstract topics in finite group representation theory. No, of course, I'm not using anything here about a particular group. This is just kind of the general topics in finite group theory. Well, what is the most, maybe the most important thing you do with a finite group representation is you have an invariant of it, which is the character. So let me remind you that if we just thought of a one-dimensional field theory was given by finite on its own, it has an invariant, which is the dimension of the vector space, which is what we attach to the circle. Now I'm going to think of this one-dimensional field theory as being something that lives in the boundary of a theory. So I'm going to think of this as coupled to this gauge theory. This is just a silly way of saying I'm going to think not just of a plane vector space, but as a representation of the group. So if I have a representation of the group, it has the dimension gets refined in a similar way. So if I have not just an abstract one-dimensional field theory, but a boundary theory, then I can define invariant just by drawing the same. There's a version of this picture. So I haven't given you all the rules of the games of the pictures I'm drawing. But one thing you get out of these rules is that the dimension of V gets refined to an element of the Hilbert space on the circle. So to a circle, remember, we attach the space of class functions. So this is addressing your question. There's a space of class functions. For every possible boundary condition, I'll get a state in there. I'll get an element, which I'll call chi sub V, which is the character of the representation. And what is this character? Well, just classically, this is the class function. So let me just give the formula. It's the thing that assigns to every group element the trace in the representation V of this group element. So this is the refinement of the dimension in the sense that if you take the character and evaluate it at the identity, you get trace of the identity, which is the dimension of V. So this is the refinement you get. So this is, Greg was upset at me for saying this. I mean, I think of this as the charge of a boundary condition, or the boundary state. But this is the character of a representation is the natural invariant of a boundary theory. And so it's something that appears very naturally by just putting my theory on a cylinder with a boundary condition. And you can keep playing these games. You can start combining all these pictures together. So for example, you can ask for the Frobenius character formula. You can ask to calculate characters of particular representations. And the claim is that representations naturally come in geometry from homogeneous spaces. So you can ask, for example, if I look at functions on a set X, which I might think of G mod K, which is a G space. So I have this representation. You can ask, what is the character? If this is V, what is the character? And Frobenius gave a very nice picture for it. You can actually see it pretty immediately. You're trying to take a trace of an element. You can think of a trace of a group element. The group element is acting on some matrix, acting on functions on the set X. The trace is the sum of diagonal elements. You think what those diagonal elements are. You quickly discover they're just the fixed points. So this formula says that all you're doing is you're counting the character value at G is counting the number of fixed points with multiplicity. This is something you can also deduce very easily from the physics. For example, you can do it in the case of induced representations and so on. So there are a lot of fun games. It's kind of a fun way to see a lot of themes in representation theory. I don't know how much we want to go. Let me just list a couple more topics. You can discover very quickly that class functions, which is what you assign to the circle, naturally are the center of the group algebra. This is an important feature. And this is why they were a commutative algebra, something that you got just abstractly from this group algebra. There's also something called the cocenter, or the Booleanization. Booleanization is probably a bad word. The technical term for this is what's called Hochschild homology. Hochschild homology, it's kind of the dual notion to center. And Hochschild homology of the group algebra. And what does that, and let me not elaborate it is, this is where characters live. So if you think abstractly where characters should live, there's a place where they want to live, which is called Hochschild homology. More concretely, you just ask for a map from the group algebra into something, which I'll call trace, and which is a universal trace. You ask for a map from group algebra to some vector space, which has a property that trace of AB equals trace of BA. That's what you'd want a trace to do. And you just look for the universal target of such a map. Where to such a map? If you just impose these equations, where do you land? And this, again, ends up being class functions. And this explains, from a more abstract point of view, why characters are class functions. So again, we realize class functions are interesting here because they carry invariants of boundary conditions, in other words, of representations. This is another well-known theme in representation theory you can discover that way. OK. And you can discover, for example, you can do character identity, the inner product identities. You can ask what is the inner product of the characters of these two representations. And anyway, so let me not elaborate more on this. So the idea is that you can reconstruct a lot of the representation theory of finite groups using two-dimensional gauge theory. And so now what I'd like to do is talk about what you can do using higher dimensional gauge theory. Or another way to ask it, what are more complicated questions in representation theory that you might hope to address? So let me start it first from the point of view of representation theory. If I give you a compact Lie group, let me denote it by G sub C, just to emphasize. If I give you a compact Lie group, basically everything I said carries through. The representation theory is very similar to the case of a finite group, except that now you have infinitely many different irreducible representations. But again, there's a two-dimensional topological field theory, which is topological Yang-Mills theory, which just topological 2D Young-Mills. Topological limit 2D Young-Mills. And all of the pictures that I drew have exact analogs. So for example, the Frobenius character formula, which I still here, I think. This is the Frobenius character formula. The Frobenius character formula in this case becomes the Weil character formula. And the idea is completely analogous. You just say, now in this case, you just fix with a single homogeneous space, which is, I'm going to look at the group modulo its torus, which is the same thing as the complex group modulo its Borel subgroup. So this is the flag manifold. So in the case where my group, if G is SUN or UN, this is the space of complete flags in Cn, complete flags of subspaces in Cn. So there's a particular nice homogeneous space to look at. And it turns out that all of the representations of the compact group can be realized geometrically on this one space. I don't even need to think about other coset spaces. They're not realized as functions, but sections of line bundles, but that's a minor modification. So any finite dimensional representation is realized by the Borel-Weil theorem, or Borel-Weil-Bott, in terms of just giving a holomorphic line bundle, on this particular space, which I'm going to call G mod B, because I'm sort of tend to live over C. So this is but it's this same space, this flag manifold. Every representation comes as holomorphic sections of a line bundle, and the character is giving the character of this representation is given by the exact same. It's a count. Well, now it's a sum, not of the number 1. It's not just counting the fixed point. It's counting the fixed points with some weight that has to do with this line bundle L. So it's a weighted sum. It's a weighted count of fixed points. And what are these fixed points? We're going to look at this flag manifold. I'm going to look at the fixed points, and I'm going to assume that G has distinct eigenvalues. Just to write the formula, let me assume that G has distinct eigenvalues, so it's regular semi-simple. Then this formula just says that I can get this count by summing over the weight of the fixed point. And these fixed points, and now let me tell you what these fixed points are. Well, you're looking at for flags that are compatible with a matrix without distinct eigenvalues. Well, the only thing you can do, well, you have distinct eigenvalues, so you have the space as a sum of eigenspaces. So if you want to flag on this, all you can do is permute these eigenspaces in some order. The only way to make a sequence of subspaces that's preserved by the group element is just a permutation. In other words, this is a sum over the Weil group. In the case of UN, the Weil group is this symmetric group. OK, so that's sort of all. This is sort of representation theory of compact groups in a nutshell. Why am I going through that so quickly? Because what I'd like to ask is analogous questions for non-compact Lie groups. So this is somehow where the representation theory gets a lot more complicated and interesting. So I'm going to look at a non-compact Lie group. Let me call it G sub R. It's a non-compact Lie group. For example, the Lorentz group. Or, you can look at SL2R. You can look at SO15C, SP4R. You can look at various. I'm going to look at a non-compact semi-simple Lie group or reductive Lie group. And I'd like to understand its representation theory. But if I give you a non-compact Lie group, it's unitary representations, for example. So these are representations that you will care about in physics, in number theory, and harmonic analysis. Big class of representations. These are now infinite dimensional. In fact, most of the representations you care about for a non-compact Lie group are infinite dimensional. And so what you'd like to understand is, what are the characters of unitary representations? How do you understand characters? And I guess I didn't do enough propaganda, perhaps, for characters. Let me remind you that, like a finite dimensional vector space is completely determined by its dimension, a representation of a finite group or of a compact Lie group is completely determined by its character. It's a complete invariant. So it's a very, and with lots of, its values are very meaningful. They have these beautiful formulas as fixed points. And you'd like to develop a theory like this for infinite dimensional representations. And then you realize, the minute you ask the question, it doesn't make any sense. Because the first thing a character does is it refines the dimension. The value of the character of the identity is the dimension. These are infinite dimensional representations. They don't have a dimension. So any naive attempt to define a character is going to fail. I'm going to tell you in a second about how Harish Chandra got around this. But maybe just to kind of give an indication of where the rest of the talk is, where we're going. So this is sort of the joint work that I'm doing with David Nadler. What we're doing is we want to capture, what we've done is we can capture the theory of infinite dimensional representations of Lie groups, of semi-simple Lie groups, including representation theory of Lie groups, including the characters. I can explain what kind of aspects of the representation are captured, but in particular, including a theory of characters can be described completely in a three-dimensional topological gauge theory. So I'm going to tell you about a topological quantum field theory in 3 dimensions, and various questions you can ask on it, which, in analogy with the pictures we drew before, capture this infinite dimensional representation theory. This is, and I can say that maybe that as a theme, this is part of this theme is, for me, was personally started from the work of Kapustin-Witten, where I explained how some of the fancier questions in representation theory, the geometric Langlands program, could be understood using 4-dimensional gauge theory, conjecturally. So on one hand, we have this ideas of how to understand fancy questions in representation theory from physics. On the other hand, there is a new kind of machinery that enables us to build topological field theories mathematically, developed by Lurie. And we kind of want to work in this middle ground. So 3 dimensions ends up being as far as we can really push this technology to right now. We can get to mathematically defined 3-dimensional field theories, but they're close enough to these pictures of n equals 4 super Young mills. Well, they're related to dimensional reductions here of this picture, and they're rich enough to capture a lot of interesting questions in representation theory. So that's sort of this is the regime where this is taking place. So 4 is kind of the goal, or maybe as we learned last week, 6 is more of the goal, but baby steps. Okay, so that's the theme. Questions so far?
Unitary representation?
It's going to be a larger class. It's the class of admissible representations, which includes, yeah. It's slightly more general, but that slight is painful. I mean, there isn't a very good geometric theory for exactly the class of unitary representations. There are smaller classes, the tempered representations, and larger classes, the admissible representations, both of which have very beautiful theories. So this unitary representations will be included in the class we discussed, but I won't be able to tell you which ones are unitary. Let me say, most of this representation theory of non-compact Lie groups, a lot of it goes back, kind of the towering figure in this subject is Harish Chandra. In particular, was a student of Dirac. So he came to the representation theory initially from physics. But Harish Chandra developed the representation theory of non-compact Lie groups very, very far. And one of the many things he did was he defined a character for representations. So, so the claim is that if I give you a real Lie group, and I give a representation V, an infinite dimensional representation, which is called admissible representation, so for example, a unitary representation. So this is a large class of infinite dimensional representations. You can define a character. You can define a character, and you say, well, what is this character going to be? And it's an analytic theory of characters. So it's not an algebraic definition like I gave before. But you say, first of all, you can define this character as a distribution on the group. So you try to define it as a distribution on the group, which is conjugation invariant. So you say, well, the character doesn't make sense. I can't evaluate a group element on this representation. I can't take a trace of a group element. But if I smear with a smooth function, smear with a test function, I can get a well-defined trace. So you get a distributional character. OK, that's not so great so far. But what Harish Chandra shows is this character satisfies a beautiful system of differential equations. This character solves, let me call it the Harish Chandra system. So it's a system of differential equations on the group that's invariant under conjugation. And what is this system? This system is says the following. It says that if you look at character, if it's an irreducible representation, it's going to be a joint eigenfunction is a joint eigenfunction for all the Casimirs of the group. For the Casimirs, or if you maybe these are in the context of symmetric spaces, these are called the higher Laplacians. Laplacians of G. So let me say just a little bit more about that. There's an algebra, which is commutative algebra, which is ZG, which is by invariant differential operators. These are algebraic differential operators on the group. If you look at differential operators in the group that are invariant under both left and right translation, you get a commutative algebra, which ends up being the center of the enveloping algebra. And your character is a joint eigenfunction. In other words, for every element z in here, there's a lambda, there's an eigenvalue lambda such that z applied to this character is lambda of z applied to this same character. This is the Harish Chandra system of equations. Or let me write it slightly more abstractly, since it would be useful. The same thing to saying is that if I make, let's introduce the ring of all polynomial or algebraic differential operators on the group, then you can formulate what Harish Chandra says is that this character, we take this character and we get a map from D to distributions where you just take a differential operator and apply it to the character. Just start differentiating the distribution in all possible ways, all possible algebraic ways. And the fact that this distribution satisfies this Harish Chandra system is the same as saying that this factors through just doing z minus lambda of z. So this Harish Chandra's statement is the same as that saying that the character defines a map compatible with differentiation between this algebraic system of differential equations. Let me call it HC sub lambda. This is the Harish Chandra system, kind of the disembodied Harish Chandra system, just a collection of all these equations. It gives a solution of it in distributions. Now, why is this so great? Harish Chandra showed that this implies that this system is a regular holonomic system. It has incredibly strong properties, and it immediately implies that chi is in fact an analytic function, not only just not a distribution, it's actually an analytic function generically on a regular semi-simple locus. And even when it's not an analytic function, it's still a function, not a distribution. It's an L1 function everywhere that's analytic away from some walls in the group. Yeah.
Sorry, are none of these differential operators elliptic? Is it still a Laplacian?
No, it has a little bit more of a feel like a collection of wave equations somehow. They're elliptic in some loci, but there's some definitely interesting singularities.
There's no Laplacian for these non-compact groups?
I mean, it is I've gone into trouble calling it the Laplacian. I mean, but it's not elliptic. It's elliptic on some locus, but it's not. I mean, there's a good version of this picture. The picture to have in mind is in for say. Well, okay, let me not.
Okay. Well, they can't be elliptic, otherwise this thing would be smooth.
Yeah. So these functions are not smooth, but they're smooth. They're smooth generically.
So what is chi?
Chi is this character, this Harish Chandra character. Sorry. So you start defining this character as a distribution, and then you find that it's an analytic function. Since Harish Chandra's definition, you find beautiful geometric and algebraic properties. Beautiful algebraic and geometric properties of this object that suggest that it might have come from algebra somehow. That it's really an algebraic object, except that the definition is very far from, there isn't an algebraic definition. So that's one of the goals I'd like to end with, is give an algebraic definition of this starting from topological field theory. So this is one of the things we've done.
For non-compact groups, the Killing forms are no longer definite. So
that's right. Exactly. And so this is so one of the results we have is a purely algebraic construction of the Harish Chandra character using these ideas from topological field theory. So in order to get there, let me just tell you one more general story, an unrelated story in representation theory that also involves system of differential equations. kind of developed in an unrelated way, but is kind of the landmark of geometric representation theory, which is a theorem of Beilinson and Bernstein. And Beilinson and Bernstein, they said that all representations of the Lie algebra of a Lie group, look at all the representations of the Lie algebra can be identified with systems of differential equations on this flag manifold. So this is what this is the collection of systems of differential equations, or also known as D-modules, on this same space, this flag manifold, the complex flag manifold. So here I'm looking at all representations of Lie algebra. They can all be identified with these systems of equations in such a way that the representations, the representations. Okay, so this is a kind of a beautiful geometric realization. It's an analog of the Borel-Weil theorem. It's somehow, before we were looking at finite dimensional representations of compact groups, realizing it in terms of this complex flag manifold. This is saying that all representations of the Lie algebra can be realized here, not in terms of line bundles, but in terms of more interesting, more complicated geometric objects. And now, in particular, Harish Chandra already explained. Harish Chandra explained the relation to representation of these general unitary representations or admissible representations to representations of the Lie algebra. He said that these admissible representations, admissible representations of the group, of this real group, correspond to what are called GK modules. These are representations of the Lie algebra which have some property with respect to the maximal compact subgroup of this real group, integrable for the maximal compact of your real group. So Harish Chandra explained this representation theory, and under this Beilinson-Bernstein dictionary, these corresponds to systems of differential equations on this complex flag manifold that are invariant under the orbits of this complex group. So these are K-invariant systems of differential equations. So for example, if you're trying to understand representation theory of SL2R, if you're trying to understand unitary representations, for example, of SL2R, Beilinson-Bernstein and Harish Chandra together will tell you you should look at the complex flag manifold, which is CP1, and you look at the orbits. You can look at either the orbits of SL2R itself, or you look at the orbits of this associated group, KC, which is SO2C. So if I look at SO2C orbits on CP1, well, that's just C star, and there are 3 orbits. And if I look at systems of differential equations that are invariant under these 3 orbits, I can recover the theory of infinite dimensional representations of SL2R. So that's kind of the geometric translation. And so one thing you can ask is, how do you understand the characters, for example, of these representations, these Harish Chandra characters, in terms of this geometric picture? And so let me. So now we need to accelerate. I want to introduce a gauge theory, a 3-dimensional gauge theory that'll capture this. And you can ask, where does gauge theory have anything to do with this? I want you to notice that the space of double cosets is something that already appeared on the board for a finite group. We had it, well, somewhere here. The space of double cosets appeared, and let me remind you that it appeared exactly in understanding intertwiners. That I said that if I look at functions on double cosets for a finite group, these correspond to intertwiners between representations. These are, in other words, maps of representations between 2 particular representations of the group. Functions from G mod B to G mod K. So this is what this. So now what this is suggesting, that I should think of a Harish Chandra module. I should think of a representation of a real Lie group. So this is one of these modules. Well, it tells me it's a system of differential equations on here. So I should think of this as some kind of intertwiner between. So this is kind of a leap here I'm making. I want to say that a Harish Chandra module, I guess I'm calling it V. This is one of my infinite dimensional representation. It defines, it's an element of these systems of differential equations on G mod B cross G mod K. And I want to interpret that as an intertwiner, as a map between all different systems of differential equations on G mod B and all systems of equations on G mod K, which respects the G symmetry. Okay, so this is a mouthful. So what I want to understand here is that before we had functions on spaces like this. Now we have these categories, which are the collections of all these systems of differential equations. They still have G-symmetry because the space has G-symmetry. And I want to ask this for all integral transforms on differential equations, all the integral transforms acting from differential equations on G mod B to those on G mod K, that preserve G-symmetry. And this is what these theorems together can be interpreted as saying. That's one way to think. It's not the way we usually think of a representation of a Lie group. But the claim is that the representation of a Lie group defines such an operator. And so now I want to identify this as some picture in a gauge theory. I'm going to attach it to the same kind of picture in a three-dimensional gauge theory. So, of course, so let me tell you a little bit about this gauge theory that David Nadler and I construct. We construct and this construction is built using the machinery of Jacob Lurie, I should say. Jacob Lurie proved a beautiful theorem, the cobordism hypothesis. It's sort of a classification of all topological field theories and all possible defects in them. And it allows us to build theories. It actually tells us to build theories from the ground up, to start from boundary conditions and move up. But let me kind of say with this in a more traditional way. We're going to build a topological field theory. Let me call it chi sub G. This is we call the character theory. The character topological field theory. It's a three-dimensional topological field theory. And, well, it's to a three-manifold, it attaches an invariant which is actually not usually well-defined. So to a three-manifold, what you'd like to do is, just like before, we'd like to do some kind of count of space of G bundles with flat connections. Connections on this three-manifold. And this is usually not a well-defined count. This path integral doesn't actually converge typically for a three-manifold. So this is not a very well-defined part of the theory. But in dimension 0, 1, and 2, this thing is always well-defined. And what does this invariant define? So to a two-manifold, to a surface sigma, this is currently under investigation. It's a little funny in this picture because we're starting, I can tell you with complete definitive what's on the point and what's on the circle. And this is something we've just figured out in the last couple of weeks, but with Sam Gunningham. But what this theory attaches to a surface is some part of the de Rham cohomology, some part of some count. But now it's a count not as a number, but as a vector space of the space of representations from pi1 of sigma into G, the character variety of this group G. Here, G is always the complex group. So this is an invariant that attaches to two manifolds. What we showed is to a one manifold. So one manifold, there's really only one. To look at the circle, to a closed one manifold, what this invariant attaches is the theory known as the theory of Lustig character sheaves. So it now attaches, instead of a vector space to a one manifold, it attaches a certain category, which is exactly, this is all systems of differential equations on the group which look like which look like the Harish Chandra system. They're all systems on the group that are invariant under conjugation and have the same singularities, the same wavefront sets as the Harish Chandra system. So that's what this theory attaches to the circle. It's a collection of all these Harish Chandra-like systems of equations. For example, the Harish Chandra system itself. So that's a particular object in what we attach to the circle. And so what do you attach to the point? Then this is the boundary. So now the main thing we've studied is the boundary conditions in this theory. And the boundary conditions in this theory, do I go till the hour? Or? OK. So boundary conditions in this theory, which is from this extended field theory point of view, is what this theory attaches. We think of it as attaching to a point. Well, before, in two-dimensional field theory, boundary conditions are themselves 1D field theories. They're coupled to the bulk. Here, these are 2D field theories that have to be coupled to a three-manifold. And a 2D field theory is something like a category. So 2D field theory is somehow determined by this category of boundary conditions in it. So these boundary conditions in a 3D field theory are special kinds of categories. So these are, so you can say what this is. These are the same as 2D topological field theories, or equivalently certain kinds of categories with an action of the group. So just like before, in the one-dimensional gauge theory, we had representations of group on a vector space. Now we have representations of the group on a category, or in fact, on a 2D field theory. And there's some adjectives you have to say. What do you mean by an action of a group on this category? And there's a theory of these, which we're developing with others. So this is the collection of boundary conditions. And so now let me sort of conclude. Well, and let me just point out that in the Lurie machine, this is actually what we stick into the machine. The Lurie machine tells you what it goes to a point, and the machine kind of grows the whole theory from there. And then you have to check what happens at every higher level. But this is somehow like giving the Lagrangian of the theory in some sense. OK, so now how is this going to help me get to Harish Chandra characters? And so let me point out that there's two particular such you can ask, OK, this is great to say that there's boundary conditions. What are examples? And the examples are the same. Everything is the same as in the finite group theory, except everywhere I saw the letter C, I replace it with the letter D. So I give you a homogeneous space, for example, the flag manifold, and I look at all systems of differential equations on this flag manifold. That's an example of one of these smooth G categories. Just like before, functions on G mod B was an example of a representation. So this is an example. And remember that Valence and Bernstein tells us that the same as representations of the Lie algebra. So if you like, there's a very natural example, which is representation of the Lie algebra. Same with any other space, like D modules on these system of differential equations on any other homogeneous space. So these are two defects, or two boundary conditions, in this 3D theory. And so in particular, you can take these and reduce them on a circle. So you can ask, what is the character of these? And you reduce them on the circle. So now I'm going to take the kind of the charge of these boundary conditions, or the character of these conditions. So I'm going to reduce on a circle, and I should get the character should live in what I attach to the circle, which are these particular systems of differential equations. So the character of a categorical G representation is one of these guys. So that kind of justifies the name character sheaves. They're actually characters of categorical representations. And the nice thing is that its character, one thing we prove, that the character of this particular representation is exactly the Harish Chandra system. So you recover the Harish Chandra system itself, the system of equations defining characters, as itself a character. This is some other guy, which we can also describe pretty explicitly. Let me just give it a name, chi sub k. And so finally, we're in a position to say, what is the Harish Chandra character? So now let me conclude by giving our interpretation. So we said that a Harish Chandra module, V, this is one of our infinite dimensional representations of the group, V defines a map from D of G. It defines an intertwiner. It defined a map from D of G mod B to G of G mod K, which is a G map, a map of representation. So in other words, let me just draw the picture. What is this boundary? So we have two boundary conditions, which I'll call red and orange, like before. So we have, this is my G mod K. This is my G mod B. And what, don't have another color here. So the representation V is something that's sitting at this interface between these two boundary conditions. The representation V is an intertwiner. It's something that has this boundary. So in other words, it's something that it gives a particular map from D of G mod B to D of G mod K. Those maps are what we attach to an interval with red and orange boundary conditions. This intertwiner gives a particular element of that. So we're interpreting this Harish Chandra module as such a map. And now we can just take this picture. And if I could draw better, this would be. So I want to take this whole picture and cross it with the circle. So now think I can't really draw. So think of taking a prism, a three-dimensional prism, which has this kind of, it's a prism with a red side, an orange side, and a white side. And I'm attaching it to ends. So this is a particular three-manifold. And the claim is that the invariant that the theory attaches to this particular three-manifold is the Harish Chandra character. What do I mean by the Harish Chandra character? It's a map from the character of this to the character of that. It's a map from. So let me just draw one final picture, and then I'll be done. So let me say we interpreted a representation of a Lie group in this very abstract way as defining a map between these two things that intertwine. Now I'm going to apply characters. In other words, I'm going to reduce the whole theory in a circle. So the character, so now I reduce on the circle. This thing we said is just the Harish Chandra system. This thing is some other system which I gave some terrible name to, chi sub k. These are two systems of equations on G mod G. And the claim is that the representation defines a map like this. In other words, it defines, i.e., a solution of the Harish Chandra system. And remember, this is exactly how we interpreted the Harish Chandra character. It was a map here, except on this side we had distributions. It was a map out of this Harish Chandra system into distributions. Now we're finding that the Harish Chandra character purely algebraically defines a map of these two systems of equations. In other words, define a solution of a Harish Chandra system valued in this particular thing. But we know exactly what this thing is. We can describe it exactly geometrically. And this is, so what you get is, in fact, is a refinement of Harish Chandra's character. Generically, what this map is giving is just an analytic function. But on the singular locus, on these walls, you're given algebraic interpretation of what is the Harish Chandra character doing. It's really giving a map of two sheaves or of two systems of equations. Or it could be said as just an invariant of the topological field theory. I told you it's not defined on most three manifolds, but here's the three manifold on which it is defined. So the invariant of the three manifold on this theory is a purely algebraic object, which, when you write it in coordinates, is the Harish Chandra character. OK, thank you.
Any questions?
Okay, well, thank you once again.
Thank you.